So we'll get started with our next speakers, and thanks to Ronnie and Nathan for letting us get our coffee and re-energize. This is normally my nap time, so if you see my head doze off, that's what it is. And just I need about 20 minutes. Um, so on, yes, yes. Well, odd that it's like that. Do you want to do the introduction? So our next speaker is Ronnie Leeper from NCEI National Centers for Environmental Information and NC State.
All right, thanks for the introduction. And also, I want to thank everybody who put this together. I know it's a lot of work to put a workshop together. So thank you for allowing me to come and not really contribute to setting that up. So this is great. Looking at my title, Incorporating Soil Context, I kind of would maybe tweak that just a little bit if I had a chance and say beginning to incorporate soil context. As we learned more, we're still facing some issues. So we'll get into that in just a minute. All right, so what do we mean by soil context? If you're not a modeler and you're taking soil moisture data from sensors, I think we've had several talks where the value of that soil moisture is very difficult to ascertain and use in any sort of like application. So if you're looking at monitoring drought or flooding potential, you really need to provide context of the soil moisture measurement. So this is traditionally done, or the easiest way to do it is if you have a long period of record, you can, over that time scale, you can compute a mean and a standard deviation, look at anomalous departures from typical conditions or normal. You could put the data through some sort of empirical cumulative distribution function and get in a percentile. These are really, really great avenues to go if you have a long period of record. If you have a short period of record, you're kind of limited to what you can do. And so you can start using the soil profile. So with CRN, we have a long period of record. We've done the historical context piece. Now we want to explore the soil context. And what I mean by that is you take soil property information and you use that to infer the value or what a soil moisture value means or how you use it in drought monitoring and flooding potential. So that's kind of our goal in this particular project. There's multiple ways to incorporate soil context. There's different algorithms. I think we've seen some presentations on that. For us, we're focusing on fractional available water. So if you were here Monday, Meter did a really good job demonstrating matrix potential, and that's what some of these values here are indicating. So for wilting point, this is roughly about 1,500 kilopascal. This is that bottom line on that graph. And then for field capacity, you traditionally use 33 kilopascal, but there's also some folks who are interested in 10 kilopascal. So we looked at both. And fractional available water typically ranges between 0 and 1. And so what's really interesting about this metric is if you apply it to your soil moisture data, you can get a sense of how well your wilting point and field capacity measures align with your station record. So that's really the main impetus of this study. Okay, so where can you get soil metadata or these wilting point and fill capacity conditions? Traditionally, you might go out when you're putting the soils in and take a soil sample. You might go in afterwards and take a couple more soil samples, and you can send this to a lab, or if you have machines, you can compute these values based on your soil samples. If you're like CRN, we have about 114 stations, and we only have about 58 of them where we got lab results back from. So I only have PET-on results for about 58 stations. The other avenue you have if you don't have access to the machines or you're still waiting on data is the USDA has a great database. So if you've heard of StatsGo or Surgo, and I think there was a presentation by the Raster Soil Survey, all that's kind of combined into one database called GNATS-Go. So we're going to be using that to extract out soil metadata information at our CRN stations. So this is my hand-drawn map and our diagram in PowerPoint. So it's a little interesting to read, but how we sample that is we take our lat long point and then we do a 30-meter buffer around the station. And this allows us to get multiple samples from the gridded database. And then for each of our depths, we're sampling over a range of plus or minus 5 centimeters. So if you look at my, over here, the 20 centimeter level, we're going to be sampling over 15 to 25 centimeters. And that allows us to extract wilting point and fill capacity. If we have multiple samples for a point, we'll do the median to kind of just average out. Okay, so where we have CRN PET-on results, we can actually make graphs of our wilting point and field capacity. And then we also pull the GNATSCO data. And so where we have both of those, we can do comparisons on some scatter plots of those values. So on the left side here, with wilting point, we have CRN PET-on results on the x-axis, GNATSCO on the y. We have a really, really high value for wilting point. If you look at 0.4, this is one of the stations where our field capacity, or our wilting point was higher than our field capacity. So we kind of have to throw that one out. But if you look in that range from 0 to 1, it's fairly good agreement, although the GNATSCO is slightly higher, slightly wetter for wilting point. If we go to field capacity, it gets a little complicated here. So we have two flavors of that. We have a 3B6 and a 3C1. I'm not a soil scientist, but this was in our PET-on results. So we showed them both here, and maybe someone can tell me, oh, don't use that one, or the other one's fine. I don't have a complete understanding of the difference between those two, but I'm assuming it's different processes of the analysis, maybe different kind of sifting of the data. But regardless, for field capacity, we see the CRN can get much wetter, or our PET-on results can get much wetter versus GNATSCO if you look at values of 0.2 or greater. We can also look at 10th bar, and it's even a stronger correlation. There are fewer stations with 10th bar results, so there's a sample mismatch there. Okay, so we've pulled a lot of different sources of wilting point and field capacity for every one of our CRN stations. And so some of the motivation for this study is, well, can we use, obviously you're going to be wanting to use PET-on results, but when you have GNATSCO, how different can it be? So we showed some scatter plots there, but it's really hard to ascertain how well these data points represent your time series. So we're going to be analyzing all these different ways to compute fractional available water to evaluate wilting point and field capacity. So we have two questions. How much better is PET-on compared to GNATSCO? Presuming one's better than the other. And then we also want to look at, is the 10th bar preferred, or is it a better match to our station time series than 33rd bar? So those are some of the things we are wanting to explore. So if we compute the fractional available water, we have a graph here of the distributions from all the different ways in which we've computed fractional available water. These box and whisker plots. The interquartile range, the 25th and 75th percentile represented by the boxes. And if you look, anything that starts with a PD is a PET-on the x-axis, USDA. This is going to represent GNATSCO. And if we have any conditions where the box is above 1, we're going to filter those out. So that means we have too many measurements above 1. It's okay to occasionally get really, really wet, super saturated, and exceed field capacity, but you shouldn't be exceeding it about 25 or 50% of the time. So that relieves about 2 options here in this particular example. And in this case, when we have that, we're going to use the largest interquartile range. And in this case, it's the PET-on 10th bar 3C1. So we can do this for every single CRN station depth. And we can look at what are the sources of the wilting point and field capacity combination that best aligned with our data. So this is where some of our results came to a pause, and we're still trying to kind of interpret these results. So we have a total of 500 different CRN station depths where we did this analysis on. Only 70 of them actually had a wilting point field capacity combination that matched our data well enough to be included. So either our fractional available water requirements that we listed earlier, exceeding 1, is too strict, or there could be some other things going on. So CRN's only got results, PET-on results for 58 stations. So we're the 570 is all of our stations. So it's a little unfair to compare the PET-on results for all stations data since we don't quite have it yet. We only have PET-on results for the 5 centimeters, so it's even more restrictive there. And then hindsight's 2020. If I could go back in time, I would redo our analysis. So Mike Pilecki did a really good job talking about the triplicate redundancy. At every one of our depths, we have 3 different sensors we're averaging together. And I did this analysis on the layer mean, which necessarily isn't tied to the soil sample that the sensors are in. So we need to go back and redo this analysis perhaps on the individual sensors, and we might have a higher sample size of 70. But since I have you guys in the room, we'll go ahead forward with this analysis and focus on the 70 station depths that we have results for. So since I was extracting out the fall, on this first graph here, I'm showing you the number of station depths where GNATs go. The USDA was selected versus PEDON, slightly higher than PEDON. But again, we only have PEDON results for the 5 centimeter level. So if we filter that further to the 5 centimeter results, this is a little more what we expect. The PEDON is preferred over GNATs go when it's available. We also wanted to take a look at the choice of 33rd bar for field capacity, which is generally what most people would prefer, versus 10th bar. Since we have a huge missampling, or not missampling, but different sample sizes, we have very few stations where 10th bar is available or computed. We redid the counts using percent. So in this case, we're looking at out of all the stations that had 10th bar available, it was chosen about 29 to 30% of the time. Compared to when 33rd bar was available, it was chosen about 12% or 11% of the time. So that kind of gives you a sense that 10th bar might be a little preferred over, at least with our data, it tends to align with our data, with USCRN data, better than 33rd bar overall. So what does this mean? So in order to begin to look at how fractional available water compares with the drought monitor, we quickly went through and matched the US Drought Monitor weekly data. I don't know how many of y'all are familiar with the drought monitor, but every week an author goes out and draws lines around the country of drought. It's represented in one of these categories: no drought, D0, which is the beginning of stages of drought, but not quite drought, and then D1, D2, D3, D4, D4 being the most severe drought. If you look at the distributions of fall to the week prior to the drought monitor map, it's actually very stable from D0 on to D3 with a slight drop in D4. Some of the reasons behind this, oh, you're fine. I'll continue talking. Some of the reasons behind this is you can be in a D2, but your previous week was a D3. So it looks like you're still kind of, the drought's not so great, but actually the surface conditions where you are monitoring the soil moisture, it's going to be a great improvement. And once I can transfer a slide, good. You can actually look at the weekly changes in US Drought Monitor. So the negative values are indicating improving drought. So this is where you went from a D3 to a D2 or a D4 to a D2. Those are the negative values there. So you see really high values of fall. And then if you go to the worsening drought, these are positive values, you see much lower fall. So this is actually really good agreement actually with the US Drought Monitor for the 70 station depths that we have. Hopefully when we get to more stations, include more, this pattern will hold, but time will tell. So to summarize, we explored a methodology to evaluate the quality, if you will, or how well soil metadata aligns with station data. And I think this is an important exercise as we become more focused on capturing and putting soil metadata into tables that are available to people, and we expect them to use it. It's probably a good idea to make sure that, hey, that data actually aligns with the measurements we have. When we looked at fall, I didn't get into this in the presentations, but almost every single station depth, the fall tended to exceed 1 more often than go below 0, which indicates that our fractional available, our field capacity is perhaps too low for the measurements we're getting from the CRN records. This is why we believe the 10 kilopascal was preferred over 33rd bar when selected, because the lower matrix potential, you're going to have a higher soil moisture value. And we also found that the measures of fall aligned really well with changes in U.S. drought state. So since we're not done with the project, I thought I should wrap it up with next steps. We definitely want to refocus in the analysis, looking at individual sensors. We believe this will allow PEDON to be more relevant and will give us more choices. There's also opportunities to look at empirical approaches that look at time series of soil moisture data to infer what wilting point and field capacity could be. There was a great talk this morning from Vinette on that. There's also some folks from Oklahoma State University, and we've used their approach preliminarily, and we found that we could add about 200. We could add an additional 278 station depths to our analysis using that approach. So too early to share any results on that particular piece of this project, but we're moving forward, and hopefully we'll have more to share later. So with that, I yield the floor back if there's any questions folks may have.
Thank you for the talk. What I'm actually a big proponent of the -10 kPa field capacity because that's what we see from a lot of field data. But beyond that, have you thought about doing any comparisons, especially if you have bulk density and texture data for your other sites that you don't have the lab data, by doing some pedotransfer functions like Rosetta or something and comparing those estimates as well, along with some of the stuff that you're looking at to see how those, how well those match with some of your what you're seeing in the field?
Yeah, so I think you're a little ahead of where we want to where we're at currently. So we're still kind of exploring the space. Once we do the individual station analysis, we'll probably circle back and look at some of those options. So maybe I think I have your card. No, I don't have your card. I need to get your card, but definitely circle back on that. It's a good idea.
That was a great talk. Thank you. Um, I love the fact that you mentioned that the field capacity that you see that might be overestimated compared to some of the legacy information that we have coming in at bedroom scale. Another thing that I noticed, especially when we are relating soil moisture to drought with the fractional available water, was that the wilting point that comes from these legacy information is typically overestimated. So what that does it in the field, the soil moisture can go much lower. So now when you're using those overestimated wilting points, you are overestimating the severity of the soil stress as well. Is there a signature or something relevant that you have seen which gives that kind of things even at USCRN sites?
So I'm still kind of working through the math on the wilting point. So you're saying the wilting point is too wet, and so we're overemphasizing drought conditions. Okay. So we haven't expressly looked at that yet. So that's a really good point, and I think we're just now beginning to start to use the wilting point and fill capacity. So to be honest, we haven't actually looked at it, and well, we're just now starting. So that's an interesting point. We have done comparisons with the drought monitor, and we do see offsets in the drought monitor in some of the soil data, and some of that's because a rainstorm came through and we see a change in the soil moisture properties, but it isn't enough or sufficient enough to change the drought status. So that's really the deepest level we've gone in terms of understanding or overemphasizing drought, I guess is what you're saying. Yep. Any other questions?
All right. Thank you, Ron, so much. That was a really great talk.